Okay, so hopefully you, if you didn't know the sublimation and deposition ones, you're able to find those. Sometimes, so the energy associated with the melting and freezing, we'll refer to that as the delta H, the enthalpy of fusion. Sometimes people will use the term fusion to describe the phase change itself. I don't like that. Like, let's just use the common names of melting and freezing because that's something we're all familiar with. And then when you're talking about liquid to gas, boiling, but also evaporation. So remember we talked about that at room temperature, you can still get some molecules turning from the liquid phase into the gas phase. It's just not going to happen to all of them until you get them to that boiling point. So that would be considered boiling. Anything before that point, so in the case of water, if you've got stuff at 25 degrees C, some of it could evaporate. That's still a phase change from liquid to gas. It's just describing it at different temperatures. And then the opposite direction is condensation. And I can't remember if I said that already. Gas to solid is called deposition. So let's just talk solid to gas first. So frequent, observation of this, probably one of the only ones that you've ever seen is CO2. So dry ice is one that at our conditions, and this is particularly at our pressures. So we will look at the end of class on Wednesday, we'll look at phase diagrams that link the temperature and the pressure together. And it'll show you how some substances like CO2 doesn't actually even exist as a liquid at atmospheric conditions that we're used to. So you would have to have it at really high temperatures. So the phase transition that we're used to seeing with CO2 is sublimation. So you have a chunk of dry ice and it turns directly into a gas as it's brought into warm conditions, and just bypasses that liquid phase. Okay? The opposite of that, which is not something we're used to seeing because you don't ever see CO2 turn back into dry ice, is called deposition. You can think of it like deposit, like the gas molecules are depositing into a solid. And with each one of these, with the red ones, there's energy required for that process to happen because that's where we're breaking intermolecular forces. Okay, so red, we are breaking intermolecular forces. So that's why there's energy required there. With the blue ones, we are forming intermolecular forces. And that's why there's energy released. There's a typo down here. This should say released. The other blue one says that. Somehow that one got messed up. So this is very much connected with what we've been doing up to this point because we're talking about those intermolecular forces, but all we've talked about so far is like relative strength. So we've said, if I have two molecules and one is hydrogen bonding and one is dispersion forces, I know the energy required is going to be greater for the hydrogen bonding. But now we need to talk about it in actual numbers. Now that we know what these numbers are being used for, what that energy is being used for, we need to do it in actual numbers and we need to do calculations with it. Okay, so most of the rest of the chapter will be kind of converting some of those concepts into calculations. So on the next page, we already did this, label what these are called. On the next page, let's look at these values that are listed here. So we're going to pretend that this diagram is for xenon. And it has these two values listed. The first one, delta H of fusion, is going to be for the solid to liquid transition. And the delta H of vaporization is what that stands for, is liquid to gas. And vice versa on these, right? It covers both directions. Because if you think about an energy diagram for going from a solid to a liquid, So solid up to a liquid. The reverse process is that same chunk of energy. It's just now being released instead of required. Okay, so if this is, 10 units of energy to go from a solid to a liquid, that would be positive 10. Whereas if you're going from the liquid to the solid, that would be negative 10. Negative because it's released. So take these values, and I want you to label the actual value, where it goes, on each of those top 4 arrows. We don't have any information about the solid and gas, probably because xenon doesn't sublimate at 1 atmosphere of pressure. So go ahead and use the delta H of fusion and vaporization and label both the red and the blue arrows, making sure you pay attention to sign. Okay, this will be for 1 mole of the substance. That's just a note for me for a second from now. Okay, so I'll go ahead and put these on there as well. So energy required should be positive. The energy released, again, same value for the one below it, but negative. And then for boiling, 12.64, should probably add units. These are kilojoules per mole. So just a good reminder of Chapter 7 stuff, that when we're talking about energy release, that's going to be negative. Okay, so interesting notes, just kind of as we're starting to deal with these. You'll notice that the delta H of fusion is lower than the delta H of vaporization, always. So it doesn't matter what the compound is, it's always easier or takes less energy to get it to go from a solid to a liquid than it is to get it to go from a liquid to a gas. That shouldn't probably be super surprising, because a liquid to a gas, you're completely severing those intermolecular forces. In a solid to a liquid, it's like you're breaking them apart, but then they just like reform immediately. So some of that energy is going to be compensated for. So you'll see a lot smaller of a value for the fusion than for the vaporization. Okay, so we're going to take these and do a couple calculations just so we're comfortable with the types of calculations we'll see for phase changes. Now, remember that when we did temperature changes, that was Q equals MC delta T. And we're going to use that again, but right now we're not talking about a change in temperature. We're saying something is already at its boiling point or its melting point. So this is like a really important point to be clear on, is that when you have a phase change occurring, it has to be at that designated temperature. So for example, for water, like you're not going to melt ice into water until you're at 0 degrees Celsius. If your freezer is at, negative 10 degrees Celsius, you can't do any calculation involved in melting that ice cube. It needs to be at its melting point, okay? So we're assuming these are at their boiling point and melting point when we do this. So go ahead and using this data above, I want you to calculate the energy required for each of these. Remembering for liquid to gas here, that would be delta H of vaporization, et cetera, okay? Pay attention to the sign and the actual value as well. I don't know why they put paper towels in the classrooms, but it ends up useful sometimes. So if you're totally lost, I'll do the first one and you can look. If not, just keep going. Okay, so check your work as you're finishing that up. So in the first one, you're saying you have just over 2 moles of xenon and you want to boil it. How much energy is it going to take to break those intermolecular forces? That's what you're calculating. So 29 kilojoules to break those intermolecular forces. And then in the second one, you've got 106 grams now of xenon, and you're saying how much energy is going to, in this case, be released, because you're going from a liquid to a solid, when that transition happens, when that solid forms. So this, think of like an ice cube forming. You stick water in the freezer, it cools down, you get it to its freezing point, which is the same number as its melting point. Keep that in mind. 0 degrees Celsius for water is the point at which it would melt. It's also the point at which it would freeze. It just depends on, are you taking energy away or putting it in? Okay? So you get it down to its freezing point, and then it's going to release 1.85 kilojoules. So release is why that negative is there, while it's turning into a solid. Because when you form those intermolecular forces, it's just like forming a bond. It's a lower potential energy, and so energy is released in that process. Yeah.
Sorry, did you say solid has a lower potential energy?
Yes. Yeah. Okay, so we are going to look at the whole process now of changing temperature for a substance as well as changing phase, because these things are happening all at once, right? I just said you can't talk about a phase change until you get to the melting point or the freezing point or the boiling point, but then how do we know the energy that's required to get us to that temperature, right? Because that takes energy too. So we're going to use these things called heating curves. And then there'll also be an equivalent, but opposite, a cooling curve that's going to look at how energy affects a particular substance, both in temperature as well as in phase. Okay, so we'll go through this in a little bit of detail, and then pretty much the rest of class, we're just going to talk through a process and use this as our guide. So we're aiming to get to this point at the end of class. We should be fine to do that. So we're going to talk through a process and do calculations as we go. Okay, so first let me just kind of describe what this chart is showing us. So we're going to start with some amount of water. It doesn't matter. The chart is generic because it's given, the units are given in mole or per mole or per gram. So it really just depends on how much your substance is. For our purposes, let's pretend right now like we're talking about a mole. Okay, so that would be 18.016 grams of water. A heating curve and cooling curve would be specific to a particular substance. So this one is for water. So let's pretend we're starting with a mole of water, 18 grams, but it's in the solid phase because we're at negative 25 degrees C. And at atmospheric conditions, at negative 25, water is a solid. Okay, so we're starting here, and we're going to progress along the x-axis by adding heat. Okay, so it's like we take this ice cube, it's at negative 25, we stick it in a pot and we turn the stove on. Okay, and we're adding heat little by little, and then on the y-axis we're going to see how does the temperature change, because that is usually what heat does, is it changes temperature. You add heat into a substance, the atoms and molecules start to move around faster, right? And that's manifested by a change in temperature. The faster they're moving, the higher their temperature. Obviously, like we've talked about before, that depends on the substance itself, how much it changes temperature by, because the specific heat capacity, that C constant that we looked at in chapter 7, that tells us, is it going to absorb heat easily and go up in temperature really fast like a metal would, or is it going to be like a slower increase in temperature because it needs more heat to raise it each degree, like water? Okay? All right, so we stick that heat in, and we actually only see a little bit of heat that we add in before we see a pretty significant temperature increase, okay? So the first thing that tells me is, oh, it doesn't take a whole ton of heat to get a change in temperature going for ice. So add maybe whatever that is, 1, maybe 2 kilojoules, and I get the temperature going from negative 25 up to 0. Then I keep adding heat, and the temperature stays constant. Like, that's weird. Why is the temperature staying constant if I'm adding heat into this system? That energy, that heat, must be going somewhere. If it's not going into increasing the temperature, where is it going? That is the phase change, okay? That energy is now going into breaking the intermolecular forces. Now, in the case of water, I might have known that already because I knew that water melted at 0 degrees Celsius, and that's the temperature where it kind of stops and I don't see an increase in temperature for a while. So maybe that's a good, like, oh, right, that's where water's melting. It's a good reminder. But now, if we see another chart like this that we don't know, it's for xenon or something where we don't know those numbers, we know now that when you see that flat line where the energy is being added but the temperature is not changing, that's where the phase change is occurring. So you're picturing the stove. You're turning on the heat. The ice doesn't look any different, but if you could measure the temperature, you would see the temperature's increasing. You get to 0 degrees Celsius, and then you start to see the ice cube melt. During that process, like in the middle of this line here, there's liquid, but there's also solid, because the ice cube hasn't finished melting yet. You keep adding heat, the whole thing melts. Guess what? Right when you finish melting that, but before any more heat's been added, you're still at 0 degrees Celsius. You're just at 0 degrees Celsius liquid water instead of 0 degrees Celsius ice, okay? Then as you add more heat, then your temperature starts increasing again. So it's this kind of weird phenomenon where you do not change the temperature of a substance until that phase change is complete. So like, for example, if you have ice in your water bottle, like you put it in there, it's been there for an hour, like you know that it's a mixture of ice and water. You stick a thermometer in there, it's at 0 degrees Celsius. Like, I don't need to know that. If I see both phases in there, I know that it's at the phase change temperature, the melting point, freezing point, whatever you want to call it, okay? Because any energy that gets absorbed, even though it's, insulated, might absorb a little bit of energy. If it absorbs any energy, it's not going to go to changing the temperature of the water, it's going to go to melting the ice. Because that's how it works. It increases the temperature, then the phase change occurs, then any additional would increase the temperature again. Okay, and then the same thing will happen when we get to the boiling point. So you increase the temperature, you hit the boiling point temperature, the 100 degrees Celsius, and then any additional heat that's added in doesn't change the temperature at all. It goes to breaking the intermolecular forces and turning that into vapor phase water or steam. So like little practical fact on that one, you can't get water, at least at sea level. I guess that would be, you would have to be below sea level to get this to happen, but you can't have water at a temperature higher than 100 degrees Celsius. So you have a pot of water on the stove and it's boiling, it is 100 degrees Celsius. You stick a thermometer in there, I don't care how long you leave it on the stove, it's not going to go more than 100 degrees Celsius. Now, boiling points decrease with increasing atmospheric pressure. So like, if you live in Colorado or something, the boiling point of water is probably more like 97 degrees Celsius. So I don't know if you are in like a cave or something, maybe the boiling point's like 101. But the point is, you can't get it past that. Any energy you add in, you leave it on the stove, you add that energy in, that's just going to go to breaking the intermolecular forces. It's not going to increase the temperature. Once you get to all vapor, all steam or gas phase, then you can increase the temperature. So you can get steam that's at 110, 120 degrees Celsius. Which is one of the reasons why, if you've ever heard that like a steam burn is worse than a water burn, it's like boiling water versus steam. That's true because, for one, the temperature might actually be higher, but also, just like with solids and liquids, the vapor phase is at a higher potential energy. So we went up in potential energy. So this is not an energy diagram. An energy diagram would be like this, right? So here's the liquid and we went up to the gas. So if you get gas on your skin, hot water vapor, it's going to condense on your skin, turn back into a liquid, and release all of that potential energy onto your skin. And that's why the burn is worse. That's also why sweat is cooling, because when you sweat, you're creating a liquid on your skin, and then as long as there's enough airflow, that liquid turns into a gas. So now we're going in this direction, up in potential energy. So it needs energy to make that phase change occur from liquid to gas, and it gets it from your skin. So it has a cooling effect because it pulls energy out of your skin in order to make that phase change occur. It's also why it works better if you're in a dry environment. If you're in like a really humid space, you're not going to get the cooling effect of sweat because it can't transition into the gas phases easily because there's lots of other gas molecules around. It makes it harder for it to. That's a whole nother thing about vapor pressure that we won't get into. But okay, so let's go through these questions and calculations. So I want to summarize what process we're talking about here because I feel like it's not very clear from the beginning. So we're going to take this 32-gram sample of water in the solid phase at negative 18 degrees Celsius. Okay, so that's our starting point. And the ending point is listed, further down, so I'm going to summarize it up here. So we're taking 32 grams of water in the solid phase, and we're going to go to that same 32 grams. Oh, sorry, I need the temperature there. At negative 18 degrees Celsius. And we're going to go to that same 32 grams of water, but now in the liquid phase at 25 degrees Celsius. And that's the process that we're going to do a calculation for to say, how much energy does this take? So this is our ice cube sitting in the pot, and we're going to bring it up to room temperature is what we're doing basically. So let me show that. I'll leave that description there at the bottom. Let me show that like in highlighter or something, what we're doing here. Okay, so starting point is negative 18. So that's that red dot. And then we're going up to 25. So the process we're talking about is up in temperature, phase change, and then up in temperature again. And we're going to calculate the energy associated with that. Okay, So the first question, does the state change when heat is added at negative 18 degrees Celsius? No. Phase changes don't occur until you are at the phase change temperature, the melting point or the boiling point. We know intuitively, not intuitively, but like because of experience, that water melts at 0 degrees Celsius, it boils at 100 degrees Celsius. If it was a different substance, I would tell you those values. But no, there's not going to be a phase change because we're not at the melting point yet. Does the temperature change when heat is added? Okay, we go back and look at our phase diagram, our heating curve. Does the temperature change? Heat is added? Yeah, this is what the y-axis is. It's measuring changes in temperature. So as we add heat, we see an increase in temperature. Yes, until 0 degrees Celsius. How can I tell y-axis value increases, right? That's the temperature. I see that line going up. Okay, at 0 degrees Celsius, though, that temperature change stops, right? So at this point, I add heat, but it doesn't change the temperature, okay? So let's pause here and just calculate what's happening between negative 18 and 0. So the way we do that is the same way we did in chapter 7. We're going to do Q equals MC delta T to find out the heat that it took to get that chunk of ice to go from negative 18 to 0. So you guys go ahead and do that calculation. Tell me the Q of going from negative 18 for that ice cube from negative 18 to 0. So in case you didn't notice, ice has a different heat capacity than water. So keep that in mind. The heat capacity of ice is 2.06. Water is 4.184. So the state does affect how it's going to absorb heat and how it'll affect its temperature change. It's easier to change the temperature of ice than it is to change the temperature of water. Okay, so 1,187 joules for this process. So let's go write that down on our picture. It's going to be kind of squishy. I'll make the ink smaller. How do I do that? Oh, there it is. Okay. Oh, it's already the smallest. Okay. 1,180. Let me write it on the other side. 1,187 joules. So that line from -18 to 0, but before that flat line happens, that's 1,187. Okay. So then next, it says heat continues to be added to the 32 grams of water. Does the physical state change when heat is added? How can you tell? Okay, so we do know that we're at the melting point and we're continuing to add heat. That would make us think that there probably is a phase change going on. We're adding heat, so we're going to be breaking those intermolecular forces and turning it into a liquid. The other way you can tell this is because there's no change in temperature. So if there's no change in temperature, like we're seeing that because it's flat, right? It's not increasing on the y-axis at all. There's no change in temperature. That must be where the energy is going. So even if you didn't know that this was the melting point, that flat line is an indicator that that's the phase change because all that energy is going into breaking the intermolecular forces. Okay? So yes. Flat line, no change in temperature, and we are at the melting point. That's another good indicator. There is not a star at the end of the horizontal line. Oh well. Okay. So these next two questions, it says there's a spot marked, ice and water will both exist. What's the temperature? There's a star at the end of the line. What's the physical state? So let me just talk through those on the picture. So it's talking about right here, that is where there is solid and liquid. So at the first point, this red mark here, how can I indicate that? This one, okay? At that point, it's at 0 degrees, but it's still ice, so it's still solid. In the middle here, it's a mixture of solid and liquid, but it's still at 0 degrees. And when I get to the end, it's also still 0 degrees, but now it's completely liquid. So throughout that change, the temperature stays at 0 degrees. And now we're going to go calculate the energy change of that segment. So hopefully you're starting to see we have to do these calculations little segment at a time. If it is a sloped line, a non-zero slope, that's going to be one type of calculation. If it is a flat or zero slope, that's going to be a different type of calculation. So when we need to calculate changes that go through a phase change, we're going to have to do individual calculations and then add them together in order to get the actual overall energy change. Okay, so that's where this this energy calculation is going to happen is right here. Let's just finish answering these questions. What is the temperature? 0 degrees, we said this. What's the physical state? Now it's all liquid. And that energy went into breaking intermolecular forces. Okay, now I want you to calculate how much energy was required to break those intermolecular forces for that 32 grams of water. Okay, so you guys do that calculation. So I'm looking for a heat, I'm looking for joules, energy, enthalpy, kind of all the same thing at this point. I need to convert this to moles because delta H of fusion is in joules per mole. And then that's going to tell me the energy change associated with the phase transition. No change in temperature at this point, just the phase itself. And that is a big number. So the other one was like 1,100. This is 10,600. Okay? Phase changes take a lot of energy. Temperature change, sure, but phase changes, that's a lot of energy there. And this isn't even the liquid to gas. That one's way more energy. Okay, and then for the sake of time, we'll do the last step together. So this one was 10,693, and now we're gonna do this last segment. So this is just liquid, but it's from 0 to 25 now. So a temperature change. Temperature change, phase change, temperature change. Q equals MC delta T, delta H of fusion, Q equals MC delta T. You cannot combine those Q equals MC delta T calculations because we're talking about liquid now, which has a different heat capacity, a different specific heat, okay? So you have to treat these separately and then add them together. So I'm now using 4.184, final temperature minus initial temperature. So it's still positive because we're adding energy in, and this one is 3,347. So the total energy for this process, heating it from negative 18 up to 25 and including that phase change, is going to be 1,187 plus 10,693 plus 3,347, or a total of 15,227. So the biggest takeaway I want you to get from this calculation is that you have to do it in 3 separate steps. People will inevitably try to do it in one, and it won't work. Okay? Temperature change, phase change, temperature change. Q equals MC delta T, delta H of fusion, Q equals MC delta T. All right, so we'll finish up 12 on Wednesday. Do you guys all remember that we have an exam next Monday? Okay, 12 is finished on Wednesday, homework Thursday, review time Friday, exam Monday. I didn't. Yeah, I didn't have an empty spot. I've been doing it good lately, so.